Okay, thank you everybody to be there today. So I have the difficult job to start. So we will start this session by some very basics introduction. As Bruno said, you are a versatile audience. So some of you will know most everything that is entitled in this presentation. But and also we will not speak about deep learning this morning. But as you will see later in the week, all the bases that you will hear this morning will be reused, and it's not so different. So we thought it was an important step to start with some kind of basics. So I will start by giving a short introduction this morning, and then we will go through a different step of machine learning, different domains. First, starting with supervised learning. And so I will share this session with Rémi Emonet. In the afternoon, we will jump to unsupervised machine learning. And then we will give you some overview on the side of method of the evaluation of your systems. So let's start by the introduction. So I will first give you a scientific and medical context of machine learning. We will go into basics this morning, but I will try, and we will all try to focus all the time on our specific application of medical imaging. So regarding the scientific and medical context, as you know, so we are now facing based on the advance in medical instrumentation and biotechnology, we have now access to a massive different sources of information to better diagnose or better understand what's going on in the human and have a better understanding of the physiopathological processes. And as for example, you will have different kind of sources going from genetic, you have different sensors also. And in this specific week, we will be more focusing on the side of medical imaging. So there has been a lot of improvement in the different types of images you can acquire, which will provide massive information that the physician has to integrate in order to improve his medical diagnostic. So this data is very huge, and what we want to do is to help the physician, not to replace the physician, but to help them, assist them in getting the most richest information, extracting the most pertinent information from this data, to so improve, refine the diagnosis, improve the therapy planning also, and also predict some type of outcome of the disease. And to that purpose, we will focus on the right side of this slide, that is how machine learning, how this mathematical domain can help getting this type of information, extracting this raw information from the data in order to predict or diagnose better for the patient. So what we want to do, okay, so what we want to do is go from the raw imaging data to what we call a decision process. So this decision is either a diagnosis or a prognosis. So what's the difference between diagnostic and prognosis? So in the diagnostic phase, we want to better characterize the pathology, whereas in the prognostic phase, we want to predict the outcome of the pathology or predict the outcome of the therapy. But the basic is the same. So what we want to do is to extract first some information from the massive raw data at the pixel level, for instance. And then there is a second step. So we will go through this pipeline, going from the bottom, from the raw imaging data, up to the decision process, what we call the wisdom, in fact. First, extracting some features at the pixel level, then going into a step that we call some kind of knowledge, meaning extracting some kind of higher level information from this information. For example, at this stage, you can find what we try to segment, for instance, some specific organs in the image. We try to detect, we can detect some lesion, for instance, in the data. And from this knowledge-based step, we then try to infer some models, what we call diagnostic and prognostic models, that will help So providing some information to the physician based on all this pipeline. So here are some examples of some kind of information we may want to extract. So at the different step of the process. First, what we want to do, for instance, is to automatically segment some organs. Here, for instance, you have an example of an MRI scan of the heart. So what you may want is extract the different cavities of the heart or the wall of the heart. So this process is very time-consuming for the physician. So one step that will help improving his task is to do it automatically. Another kind of information you may want to do is try to predict. For instance, here you have some modeling of the heart, and you want to predict the lesion based, for instance, provided by an infarct on this heart. And based on the strains, that is how the heart will contract. And this information, you will get it already. It's already a process phase that you will get from the raw image, from MRI, for instance. Another thing that we want to do, for instance, is to detect some pathological case from the normal population or from some types of population. So detect outlier that may be a different step of the process. For instance, during a diagnostic phase or from preventive medicine, you want to see if some people is getting out of the regular path of evolution, okay, from a normal population. This is some kind of process you may want to do. So now we will look more specifically at these different steps. So going from the raw image process, as I told you, up to the decision, and see how machine learning how machine learning processes for this pipeline to analyze this medical imaging data. So now I will go to the second step of my presentation, that is explaining you in a few words the basics of machine learning. So as I told you, the first step to do is to decide what you want to do. So you have to define a task. So what do I want to do what do I want to extract from my image? I want to segment something, I want to predict something. So the first thing to do is really to define the task you want to model. Second thing, you have to formulate this task as a decision function. So we will go into this different step, but this is very basics, but you have to really formulate this, take time to formulate what you want to do, then try to model that in a mathematical form. Then once you have your model, so mathematical model, you will learn the parameters of your model based on your data. So you have the basic of machine learning is that you want to learn something from the data. It's at the basis, as I told you. And when you want to learn that, you have also, if you want to learn something, you have to decide when you learn correctly or when you learn badly. So you have to define what we call the performance metric. So the model will be learned according to some kind of performance metrics you have to decide. And when you have completed these 3 steps, then your model is ready to be used, and you can, at this step, infer some decision from this model on new samples, on new imaging. So now let's go back with some example to these different steps. So first, I said you have to define the task you want to perform. So for example, in this image, so it's a brain MRI, T1 MRI slice of the brain. Let's say I want to detect some lesion. I think there is something wrong in this image, and I want to automatically detect some lesion. So the task is detect. So it's a detection task. Second, you have to formulate, as I said, this task as a decision function. So what do I want to do? If I want to detect some lesion in this image, I want to decide whether each pixel of this image is a lesion or a normal tissue. the objective, for instance, here is not to classify. My objective is not to classify this slice, saying, okay, it's pathological or it's normal. No, I want to locate. I decide my objective and my task is to locate lesion in this image. So I want to decide at the voxel level here, for instance. And so my task is, can be reformulated as a classification task. So I will say this voxel is a lesion or this voxel is from a normal tissue. So from the mathematical point of view, it will be referred to as a binary classification problem. Then, depending on the data I have, what kind of data I have, this problem, this classification problem, will be considered or will be referred to as a supervised learning problem or an unsupervised learning problem, or in between what we call the weakly supervised learning problem. So in this talk, as I told you in the introduction, we will cover the different steps of machine learning. And as you see, I said that I will first start with a supervised learning problem. So this will depend. So these different types of domain will depend on the types of data you have to learn your decision model. So the second step, so I say I want to perform a binary classification problem. And now I have to look at what type of data I have to perform this task. In this example, suppose I have some reference database. So I have some images where I know the lesion, where some physician, as you say, it's very small here, pointed out some lesion in the image. So I have what I call the training database, an annotated database with not only one example, as I can show you here, but some samples where I know the raw image and I know the reference of the lesion. So this is called the training database, and I can use that to learn my model. In this situation, I am in a supervised learning problem. Supervised means here that I know I can give my model some information to help him learning what he needs, the task he needs to perform. So I have some reference information I can input to my model to say, you have to detect this lesion, and I know where it is, and please try to detect the reference lesion I put you in. So now you have, in this situation, based on the data you have defined that your mathematical problem is a binary supervised classification problem. So then, what you need to do is design your model. So we'll see later in the course how you can design your model, but there are two different steps, two main steps you have to decide. First, if you have to decide what type of information you will extract from the raw image. So it's called this step is called the feature extraction step. So what type of information can I get from my image? I can just decide to use the raw intensity level in my image as a feature, or I can do some kind of processing to extract, for example, some texture from the image. So this step is called the feature extraction step. When I have done this, then I am in a mathematical configuration where here, for instance, all these points are example, for example, image corresponding, so the raw image has been transferred into what we call the feature vector. Here, for instance, the feature vector is of dimension 3. And all this image now are in this, what we call representation space. In blue, I have, for instance, some normal voxels, because I am, as I said, I am supervised. So I know that from my training database, I extracted some features. So the blue point correspond to normal voxels, and the red points here, for instance, correspond to abnormal pathological voxels that I can extract, again, from my training database. So the purpose now, in this space, so I said, for instance, here it's a three-dimensional space, I need to separate, what I want to do is to separate the normal voxels here in blue from the pathological voxel here in red. And this is a problem to learn what we call the decision function. Here you see the decision function is a green hyperplane here. And what you want to do is to learn the parameter of this hyperplane. Once you have this, if you get a new sample, you would then project your sample into this representation space and look if your sample is on the right side of the hyperplane or on the left side. Okay? So once you have designed the different elements of your model, so which feature you want to work on and which classification model you want to learn, the third step is to learn the parameters of your decision function. And as I said in the beginning, to learn this model, you have to define some metrics, some performance metric. So when do I know if I correctly define the right model? So what we call the performance metric, we can here call it, for example, a loss. For instance, in this case, you will input a training image in your model. The model will classify the voxel of your image, produce an output, and you will have to decide if this output corresponds to the reference image corresponding to your input. Okay? So here you have to compare these two images, and at this step you have to decide a performance metric. Do I reproduce correctly what I have as an input or not? So this is the performance metric. You will define some error from the comparison of these two images. And based on this error, you will modify the parameter of your system to improve recurrently the output and to make it better fit the reference you have in your training database. So this is the third step, that is called the learning phase of the decision model. Then, when your model is learned, you can infer some decision from the new sample. You are ready to use your model to test it on your data. So take a new data, project it, extract some feature as you decided, project your data in your feature space, and based on the decision models that you have learned, decide if each voxel of your data is normal or a lesion. So this is really the basics of supervised machine learning. Well, in this case, it's supervised machine learning, because, as I said, I decided in this sample that I have in my training database some reference, I have some information on the things, on the task I want to perform. So what is deep learning now regarding this big system? As you will see, well, it's a very oversimplistic way, but just to say that deep learning is just a subpart of machine learning. And what you want to do in deep learning is you want to combine this feature extraction and classification step. Instead of manually deciding which feature you want to extract at this step, you want to learn the best feature from your data directly. So you will combine these steps with the classification step, so make some return, and at every time you want to compare your output with the reference, you will both modify this feature extraction and the classification altogether. So it's very simplistic, but it's just to kind of de-dramatize what deep learning is compared to machine learning. So it's very closely related, and that's why the course you have this morning are not so different from what you will hold the rest of the week. So just before getting now into the principle, more in the principle of supervised machine learning, I want to give you some highlights of artificial intelligence, historical highlights. So it's very short and naive, of course. Again, just to locate the different concepts of what we call artificial intelligence, machine learning, deep learning. So artificial intelligence encompasses all these kind of subdomains. And you will see that historically, for the first systems, what we call the first expert system and the first neural networks were born around the 50s. And at this time, there was two kinds of artificial intelligence, what we call the symbolic artificial intelligence and the connectionist artificial intelligence. To be fair, from an historical perspective, I should have put like a growing, increasing line saying that at the beginning, symbolic artificial intelligence has a higher weight than the connectionist AI. So connectionist artificial intelligence is equivalent to machine learning. So the difference between symbolic and connectionist is that at this step, symbolic, the first people who work on the domain think they wanted to reproduce the brain. So they derived some system where they try to put the human intelligence into systems. So it was what we called expert systems. So they defined some rules, some decision rules, and they kind of feed that to big system, which were based on symbolic links and infer new decision rules from the ones that were fed to the system. On the opposite, connectionist artificial intelligence or machine learning aim at reproducing tasks, as we went through the basics, from learning some specific tasks from the data. So going through the years, so the symbolic artificial intelligence tends to decrease. The importance of symbolic artificial tends to decrease, whereas machine learning is increasingly be used. In the 80s, there was a big area of neural networks, for instance, and also machine as support vector machines, kernel machines that we will learn a little bit later. And as you see, almost 10 years ago, there was a big jump to what we call deep learning, so which is again a subdomain of machine learning. So you see standard machine learning now is still alive, as you will see, but there was a big jump here. And it was specifically based on the developments in graphical GPUs, for instance, the computer efficiency to process some data, and also based on the data, because the system, as we say, learn from the data. So they need to have access to massive amount of data. And based on the web database that were created, for instance, ImageNet, combining to the improvement in the computational efficiency of the GPU, graphical cards, for instance, this was a big start from deep learning that we will see all over the week. Deep learning in medical image analysis also. So there was a big jump, as you can see here. So these charts are extracted from a paper from 2017, so it's already a quite old paper. So you will see that starting in 2012, there were only very few papers related to deep learning. There was a big jump here that is still increasing from 2016. And regarding the domain of medical image analysis, deep learning now is covering every kind of medical imaging modalities. With we can see a big impact in MRIs, but all kinds of medical imaging are covered. All kinds of pathology also are covered. And as we say, machine learning is used, and deep learning specifically, as we say, to extract some information or some knowledge at different steps. As we can say, there is a lot of things to extract some, do automatic segmentation, also to detect different kind of lesion. We can also use deep learning to perform classification at different level, at the image level or at the voxel levels. So every areas of image processing are covered, every pathology and every medical imaging modality. I don't know if you have some question regarding the first part, but you're very quiet. So I will jump to the, now start getting more into detail in supervised learning. So I will make the introduction and go to the first part. So again, we'll start kind of repeating same thing, but as I said, it's very important. You will see for those who didn't try to do some machine learning again for their medical image analysis problem. It's very important to take time to define what you want to do. So again, I repeat, you have to define, as I say, what is the task you want to perform automatically. Once you have defined that, it's more simple. It's really more simple when you're clear with what you want to do exactly with your data. It's more simple than to define, to model it as a mathematical function and to be efficient. So here, suppose again, we want to automatically segment hippocampus here in the brain. And for this, again, so it's a very similar use case as the one I showed you before. Suppose you have already some training data where the physician manually annotated the hippocampus in the image. So again, we say it's a supervised classification problem. And again, so what you want to do is automatically process this image. So you want to determine if each pixel of the MRI belongs to the hippocampus class or not. So it's very similar classification problem as the one we have seen previously. So as I said, so you have an annotated learning database. So you are in the context of supervised learning. So from your data, so you have the set of training database here. And for each voxel, well, here it's each patch, for instance, in the image, you know if this patch belongs to the hippocampus or not. So in this case, we have a binary classification problem. So we have two classes. So you can extract different patches from the normal class and patches from the hippocampus class here in blue. So one where you have done this feature extraction step. Here, for instance, in this situation, the feature vector is a patch. So for each voxel, I will consider a small patch around my center voxel. And I will say that the feature vectors is the intensity of all the voxel in this patch. So if I have a 9 by 9 patch, for instance, the feature vector I will get is dimension 81. So this is my feature representation. Here on this sample, it's very simple representations. I've only looked at two features. And in this feature space, so I will have, again, the blue point corresponding to the hippocampus and the the green point corresponding to the normal structure. And my purpose is to learn here a decision function that will separate the blue points from the green one. So again, I repeat it. So the first step is the information step, and then what we call the knowledge steps, where we want to learn the decision model. And again, during the inference step, you will take a target patch, project it into the representation space, look where it's located, and label, and you can then label the target patch. So now I will introduce some notation. So as we said, so there is a standard pipeline. First, you have your data. Then you will extract some feature from your data. So I will go from image here to what we call the feature vector. In all my presentation, I will, the feature vector, so here will be represented by xy here. So it's a vector of dimension d. So as I said, for instance, if I consider this patch as a feature vector, and if here I have a patch of 9 by 9 vectors, G will be equal to 81. And I will say that each feature vectors of my training database is associated to a class or a label here. And here, Y belongs to, is an integer, for instance. So it's corresponding to the different class. It can be, so here, for instance, if I have 3 classes to consider. So based on this notation, here, again, for simplicity of visualization, my feature space is of dimension 2. And I have projected all these all these training batches in this space. So with the different colors corresponding to the different classes. And my purpose then is to find a decision function here that will separate the space, the representation space, into 3 regions here corresponding to the 3 different classes. So the first step that we will not go too into details this morning is you have to make sure when you want to do some classification is that you have to perform some pre-processing of your data. So we won't really develop the part of the paper, but when you take some raw images, you have to be some kind of normalization, of course. Some kind of thing, for instance, if you consider how here different heart shapes extracted from some patient, you can see that you cannot really compare these different shapes because there is a high intersubject variability. So if you want to make some prediction, in general, you have to do what we call spatial normalizations. It means you have to, if you can, project all these spaces to a common template to derive an average geometry. So it's a spatial normalization. You can also have to define, if you are looking at time series, for instance, here, to perform some temporal normalization in order to be able to compare the different graph, the different curve from different patients. So this is what really an area that we will not cover in this talk, but it's important to know that you have to ask you before starting if your data are ready to be analyzed or if you need to do some pre-processing. So second step, as I say, is you have to extract some feature from your data to go in this representation step. As we said, the purpose of deep learning is to automatically extract the data from your raw image. So we won't take too much time on this step also in this course because it's not the purpose exactly of our course. Just as an illustration, here are different things you can, if you want to do standard machine learning based on manual extraction of feature, there are lots of different types of feature you may want to extract from your data. First, basic things, as we said, you can work on the gray levels, on the intensity of your image. You can go to the second order statistic, extracting some what we call texture parameters from your data. But you can also work on more higher levels descriptors. For example, if you consider here again some geometry, if you can access to some parameters on the geometry of your organ of interest, you can look at some fibers, extract some fibers, or here extract some mechanical parameters from your data. And also, importantly, in our field, physicians are really sometimes have a very good understanding of what is discriminant in their image to help localize some pathology. So you can also decide to extract some very clinical parameters that from your data. So now we will focus on the last part, which concerns how to learn the decision function here. How to model and how to learn the decision function here. So we suppose now, for the rest of this talk, that we went from the raw image to the representation space here. So we are now working with X and Y. So X feature vectors and their corresponding label. And we want to learn here these different curves in the domain. So for the rest of the talk, we will mainly focus on binary classification. I will just make some comments here that in our talk, so as I said, we want to learn some decision functions that will separate labels of different class. In this context, we say that we have a label for each vector, but this label doesn't correspond to any biological thing. It's just a way for us to say, okay, I will put y equal -1 for the pixel corresponding, for instance, to normal tissue, and y equal to 1 for pixel corresponding to lesion tissue. Okay, but this value here of y doesn't mean anything biologically. It's just a convention of notation to help us doing this classification. So when sometimes you may want to do some regression, that means in this case, y has some meaning. You want to estimate the shape or the you want to estimate some dimension in your image. So y has some physical or biological parameter. In this case, we will talk of regression. But what I want to say is that in both cases, the mathematical foundations that underlie these two types of tasks, so classification and regression, are similar. So in the rest of my talk, I will mainly focus on classification, and I will also focus on binary classification. So we see that there is an extension to multiple class classification that is that we can talk at the end of the course, but all the following will concentrate on binary classification. So what we want to do is to learn now a decision function that will map our input, so our feature vector x, to the output, so the label, the class. And for that purpose, we have a series of training data samples that we call here. It's a couple of x, y, and xi and yi here that I will use in my situation. So directly, f doesn't directly output the class. F, the functions that we want to learn, will either be a scoring function that it will go here from, so the parameter x to, for instance, sign distance to the hyperplane, or f may be a probability of belonging to class y. Okay, and so from this decision function, we will then apply a decision rule to extract the label. So y here will be extracted from some decision rules that we apply to the decision function. So generally, so as I said, the decision function is either a score or a distance generated to the decision function we want to calculate, or a probability. So what is supervised learning in a nutshell? So very basic. So first, when you want to learn a decision function, so you have your sample data set. What you will need to do is to separate your data sets into 3 parts. First one, that is called the training data set, on which we will learn your model. Then there are another 2 data sets. So the validation one that will help you tuning correctly the parameters of your model during the training step. And then the test data sets that will serve you to evaluate the performance, the global performance of your model. So first thing to do is to decide how to split all the samples data you have to learn your model. Then, as we say, you have to choose a function a model function that generally is parameterized with a set of parameters θ1 and some of hyperparameters θ2 in some cases. So we'll go into more details of these steps later in the course. But suppose you have different kind of decision functions, so you will have first to pick one of your decision function. And this decision function, as I said, have some kind, is parameterized by a set of parameters θ1 and some hyperparameters θ2. So what is the difference between parameters and hyperparameters? Hyperparameters are parameters that are tuned by the user, whereas parameters θ1 are parameters that will be learned based on the training sample. So when you have choose your model, you will first fit the model parameter θ1 based on your training data set for a fixed value of θ2. So the user, as a user, you decide to fix some values of θ2, and you will then learn the best value of your model θ1. As I said, during the learning step, you will like to define a performance metric, an error function that will measure, estimate the misfit between your decision function and the class. And all the purpose of the training will be to, as I show you in the first slide, to minimize the error functions, so that your estimated class corresponds, best fits the reference class of your training model. So once you have done that, you will get to one first model corresponding to the hyperparameter value of θ2, and you will then evaluate the performance of your model on your validation data set. Then you will select another values for your hyperparameter set θ2, and you will retrain your model again on this function. And again, evaluate the performance of your new model corresponding to the new value of θ2 on your validation data set. And when you have covered all the range of hyperparameter value of θ2, you will select the best parameter set. And once you have selected this parameter set, you will then can be able to evaluate the performance on your model on your test data set. So now we will focus on this training stage. So we are just working with our training data model, training database, and we suppose we have chosen a fixed value of our hyperparameters. So how to choose a decision function? As I said, there are different models of decision functions, and how to choose your models. So there are two different approaches. So you can decide to choose a linear models. So it will try to define linear hyperplanes in your data, as I illustrated on the image. Or you can decide to work on nonlinear models. For instance, in these types of models, you will find the neural network. You will find decision trees, for instance, kernel machine. In the linear model family, you will have the linear support vector machine, for instance, logistic regression, or linear discriminant analysis. Then, so depending on this type, you will have a classification of your different decision models. Then another way to discretize the different types of models, they are based on a different strategy to minimize the error functions. There are some models that will do a global minimization on the original feature space, what I call the representation space. And some other models will do a recursive minimization. So they will do some minimization considering only smaller parts of a reduced part of the original feature space. And you will see that later on in this course regarding what we call decision trees. Then, again, when you decide to, regarding the panel of all the decision function, there are different types also of error function. as I said, you have to decide which kind of error function. So one of the error function of the type is based on the classification, on the minimization of the misclassification error. And this is a type I will develop just after this introduction. But there are also some other functional you can decide to minimize. And depending on the choice you will make at this step, it will determine different types of models. So just to give you an illustration, so here are the basics, different models of learning function you can have, depending on these different architectures. If I want to do global minimization, if I want to use a linear model, here, for instance, you have different models. And if I want to do global or minimal minimization of the error risk. So here, for instance, on the left, you have some illustration of a binary classification problem. So it's very simple. And what I put here in different colors, that corresponds here to the different steps, because it's not easy to see, is the performance of different classifiers belonging to these types of these families. So here you have the performance on a linear classification task, and here on the right, on the nonlinear classification task, and you can see that some model performs better or less depending on the task and on the model. So you will see it better tomorrow. So tomorrow afternoon, you will have an end-on session where with Nicolas Duchâteau, and you will be able at this step to manipulate these different types of classifier on a real application here on the analysis of different cardiac shapes to perform a classification task. So you will be able to compare different kinds of models to better understand. So now I will briefly introduce one kind of family of models that are based on the minimization of the misclassification error. So how does it work? So in statistical decision theory, learning theory, we refer to the notion of risk or the notion of prediction error. And under this framework, in this framework, we decide to, so we have, at this step, we have chosen a model for the decision function f, and we want to tune the parameter θ1 of this decision function. And we say that in this type of model, we will decide the parameters that will minimize the prediction error between the estimated labels derived by f and the true. So this is represented by this equation. So we will decide, we will choose the function f that will minimize this quantity. So this quantity is a sum here over whole, well, first before, we have to define what we defined a cost function associated to f that quantifies the cost of doing a prediction error. When do I do a prediction error? I do a prediction error when f, well, it's not exactly f, it's d the f, because it's a decision based on the score, is different from the true label class. So L will quantify the cost associated to a prediction error. For instance, if S correctly predicts Y, what do you think of L? Should be L be a high value or a small value? Small. Good. You are not noticing. Okay. Good. So the loss function, the cost function will be low if I predict correctly the class, and will be high if I want to penalize the function that will make some error on the prediction of f. So the risk associated is a summation over all the cost function here, modulated by the probability of jointly observing x, y, and y, x and y. So it's what we call the joint probability. So it's very difficult in our situation. We have only access to some training data points. So it's very difficult to extract, to estimate this joint probability function here at this stage. So estimating what we call the risk is a very tricky problem. So what we generally do to work with, within this framework is we will estimate f. One way we can do is to estimate, to try to make some assumption to estimate that, and then derive the probability directly estimating what we call the posterior probability density. But the most simple, another way to do it is what we call to learn discriminative models, is to estimate f directly without estimating this joint or these posterior probability densities. So we want to model directly the decision function. And the way we do that is we go from what we call, as I said, the risk here, to the empirical risk, where we will estimate this risk over our sample database. Here, I will go from a continuous integration over the joint probability to summation here over the learning data samples that I have. So it's the same, almost the same equation, but here I will directly sum over the cost function here on my number n sample database. And so I will choose the function f that will minimize this quantity that we call the empirical risk. And again, as you say, this function is based on what we call a cost function that I have to decide. So there is a difference in estimated the empirical risk compared to the risk again. As you see here on this axis, you have the complexity of the function. So I can, as I say, have to decide, I have to fix some kind of function. I want a class of function. And as you can see, depending on your model, the best function that will get to the minimum risk will not converge exactly at the same point regarding the empirical risk and the risk. So when the number of samples tends to infinity, these curves should converge. But for a fixed size, the empirical risk and the risk converge to a minimum but may be different. So here is a better illustration. Suppose, for instance, so it's some kind of illustration to explain this notion of complexity. So suppose you have a training database here on the left with the blue. You want to separate the blue and the green points, and you suppose you have decided you choose two different decision models. So the purple one is a linear separator, and the red one, as I say, is a more complex shape. So the complexity of this F2 function is higher than the complexity of the purple function. So on the training database, as you can see, increasing the complexity, you can go to an error on your training database that is 0. For instance, here, if I look at the F2 function, all my points, the blue and the green one, are correctly classified. So I have an error function on the training set here that is 0 here I put the number of misclassified points. So sorry for the color, it should be blue. I have some mistakes, but okay. Whereas if I consider the purple curve, as you can see, if I look on this side, I have 3 green points here that are misclassified, and on the bottom part, I have again 3 blue points that are misclassified. So I have a prediction error here that is higher than the one on the F2 function. So I will say the more complex function I get, if I try to use the empirical risk minimization, I will say, okay, this function is better because I have a misclassification error that is lower. But now consider that you had some new samples from your distribution. So here I have the training database I used to fit my models, and here I put some new samples. So in this situation, if you consider your same function, you will still have a zero error on your test database, okay, because my distribution was correctly estimated. Whereas if I consider that my true distribution of data is more in this configuration, then considering now the 2 models, the F1 and the F2 model, as you can see, I will see that I have 8 points that are misclassified with the F1 model, whereas I will have 10 points here that are misclassified with the F2 models. So meaning that you can, if you just consider the empirical risk, you can increase the complexity of your model up to achieving a null error. But going to the evaluation on new samples, then you will not, what we say, generalize well. We will have a model that will overfit your training data, and that will not generalize well to new sampling, that may not generalize well to new sampling data. So in fact, you have to compromise what we call the empirical risk and the complexity of your model. So in fact, what we do is, instead of trying to find a function that will minimize only the empirical risk, because this is the left part of your model here, you will add a regularization function to your minimization problem. And this regularization function will try to tend to make the complexity, to control the complexity of the functions that you will learn in order to improve the generalization performance of your model. Okay, this is called, in fact, the structural risk minimization. So to solve this function now, based on these models, and as we say, okay, so the general problem is now to find, you want to find the function f that will minimize these things. So first thing you have to do is to say what is the shape of my decision function. Okay, I have to model my decision function, then to be able to parameterize, to estimate the parameter of this function. So usually, and in most of the situations, we will consider a linear decision function. So we will say that this function is parameterized by 2 parameters here, omega and b, so which are the parameters of the hyperplane in this space dimension. So the parameter, this function is parameterized this way. And then you have to make also some hypotheses on which loss function and which regularization function you want to use. So just some notation. When I write that my decision function is of this form, this is the equation of the hyperplane here in blue, corresponding to fx equals 0 here. And if I consider a point, so w in this equation is normal to the hyperplane, and b is the distance from the hyperplane here to the center of my space. And if I consider any point here in this dimension space, the distance of this point to the hyperplane is related, is f the x normalized by the distance, well, by the norm of omega. So it's important because, as I said, the decision function f is usually a distance from the hyperplane. So in this case, you see that my decision function fx will be related to the distance of these points to the hyperplane I want to estimate. And so it's just some mathematical reminders for the following. And another thing we said is that usually, and it's a convention, in a binary classification problem, we usually say that the class Y is generally +1 for the positive case, as I said, and -1 for the negative case. In this situation, consider this point here. If I have the hyperplane F1 here, so this hyperplane is a signed hyperplane. So if I have on the side of the same side of the orthonormal vector here, W, I have a distance here that is positive. And if I am on the opposite side, I have a distance to the hyperplane that is negative. So in this situation, if my point, if I here have this point, this blue point, so it's badly classified, okay? The class of this point should be 1. And if it's badly classified, here the distance to the hyperplane is negative. And in this case, if the class here is 1, the product of the distance to the class when I am misclassified is always negative, whatever the position of the points compared to the hyperplane. Whereas if I am correctly classified, the product of the distance score with the class is always positive if my point x is correctly classified on this scheme. So it's another convention that is important for the following. So as I said, so you have to make some assumptions. We say, okay, f will be a linear hyperplane. Now I have to decide which loss. I have to decide the loss function. As we say, the loss function quantifies the error that you commit between the predicted class and the true class of your model. So as we said, the product y multiplied by fx is positive, always positive, when the point is correctly classified. So if the point is correctly classified, I will say we will have a loss function that should be low or even 0. If my point is correctly classified, the loss of classifying f the x correctly as y should be almost null or very small. So here on this graph, you have a representation of the different types of loss function you can find. So it's here represented by the loss of y and f as a function of the product here, I multiplied by f. So for instance, consider the standard loss 0, 1. As we said, when my point is correctly classified, I should have a loss function that is null. Here I have 0. Whereas when I have some error, prediction error, so this product here is then negative, then my loss here is constant. I have a regular weight of 1 for all points. Whatever the distance, here you can see that on this axis you have the distance to the hyperplane. So when I have far on the left here, I am close or am I far from the hyperplane. So here f, as we said before, f here is the distance to the hyperplane. Okay? The farthest you are, the biggest f is. So when I go on the right here of my on my graph, it means I'm regarding at points that are correctly classified but very far from the hyperplane. When I'm going very far on the left of my graph, I'm taking a green point here that is very badly classified, so it's very far from the hyperplane. Okay? Sorry. So here, for instance, the farthest I go here on the left, it means that my point is very badly misclassified. So what I want to do here with the blue loss function, the weight, the loss function, is independent of how badly my point is misclassified. Whereas if we consider the other function here, for instance, the hinge loss, you will see that the farthest I go, the more weight I put on the loss function here. I want to penalize the points that are very badly classified by my classification step. So here you have different variants, so of the classification loss. And you see, for instance, that you have the hinge loss and the logistic loss that are quite close here on the classification step, whereas the quadratic loss that will put some very heavy weight on the points that are really misclassified. Then you have also to choose some regularization functions. So I won't go into deep details on this, but generally what we use for regularization when you have a linear model is you consider at omega, so the regularization function, as is taken from the family of the LP norms, and usually you use the norm L2 to add to your model. So now you have defined most everything. So you have chosen your loss function, you have chosen your regularization function, you have chosen some function, some form for f, and you will have to fit the parameter of your model by solving this minimization problem here. In general, there is no closed form solution for f, so you will have to solve standard an optimization problem. Generally, you try to take L and omega as convex functions so that you can reformulate this minimization problem as a problem here, a quadratic problem under a specific constraint, and for which we can use standard optimization algorithm. So we won't go into details at this step on this part of optimization. Just to give you some, je sais pas l'heure qu'il est. C'est quelle heure? 11h38. Merci. Just to give you some illustration of one typical model, that is a linear support vector machine. I want you to make the parallel between the loss function, what is called the in-loss function, and some more geometrical insight. As you can see, when we have a separate classification problems that is quite simple here, you have problems that are linearly separable. You can have, if I want to find the hyperplane here separating these two groups of points, I have an infinite solution. I can draw as many planes as I want. So this problem is not, it's an ill-posed problem if I don't put some more constraint on the problem. So what I can decide is to derive the hyperplane here that will maximize the margin here, represented by this space here between the two green lines, the margin between the training sample of both class. So I want to find the hyperplane here, that is the straight line here, that will maximize the distance here of every point of both class to the margin. So the margin is a smaller distance of any training sample here to this hyperplane. So I put some constraint on the hyperplane I want to build. So how can I formulate this problem? I want to formulate this problem. So I want to find the margin M. So I call it M, the margin. I want to find the maximum value of M under constraint that all my points are correctly classified. What does it mean? We say that we want, so this, as you say, is the distance. You remember from my previous slide, this is the distance to the hyperplane. So I want that all my sampling points here lay at a distance higher than M. So, and as we say, we have again the product of y multiplied by, this is the fx, and I want this, so this distance, to be higher than M. That I want my point to be outside this tunnel here, corresponding to the margin. So this is a problem formulation. In fact, it's a ill-posed problem, because if I find, so I want to find here the value of V and A that will maximize this problem. These are my, this is the value I want to, the parameters I want to tune from my training sample. So this is a kind of a ill-posed problem, because if I find a couple V and A that is a solution of this problem, then whatever K value, positive value, I will have this key V and key A couple that will be a solution of this problem. So by defining change of parameters, putting W is, on this form and B normalizing here by the norm of the problem, and replacing V and A in this formulation, I can come to what we call the canonical problem formulation. And in this situation, you can see that the margin, with this definition, I have the relation here between the margin, M, and the norm of the hyperplane here, of W. So when I want to maximize M, in fact, it's corresponding to minimizing omega, the norm of W here, sorry. So I won't go into detail, but you can jump from the previous formulation to this, what we call canonical formulation. So in this situation, I have the same problem formulation, but in this case, the product here is, I want my point I correctly classified if they are outside this tunnel, and the distance here of this tunnel is now equal to 1. So if I take a more complex problem, so here, for instance, compared to the previous situation, I have two other points here, a blue one. I had it the blue and this point here. And as you can see in this configuration, my problem is not perfectly linearly separable. I cannot find a plane that will perfectly separate these two sets. So in that configuration, I will accept, I will say, OK, I still want to find a linear hyperplane, but I will accept to commit some error, and I will model this error by what we call slack variables xi here. OK, and these models, these variables will estimate, will measure the distance to the margin. OK, I will say that if my point here is correctly classified, I have the product here that will be higher than 1. So I am out of the margin, so I am higher than 1. And in this case, I commit no error, so xy will be equal to 0. In the other case, corresponding, for instance, to the blue point here, x, this point is not out of the tunnel here, to the green tunnel here. So the distance, the product here, is smaller than 1. And in this case, I will model the error as a distance. This product here is a distance to the margin, so here to the hyperplane. And I will say that the error is 1 minus this distance. Okay? And if you look at this expression, in fact, we can say that the error xi1 is correspond to the max between 0 and 1 minus this product. And this corresponds to the hinge loss, in fact, that we have defined here on this graph, saying that if, in fact, you cannot see very well, but the hinge loss is a straight line here, up to the value of the product equal 1, and then it's null. So the hinge loss corresponds exactly to this problem of support vector machine, trying so to find this mathematical hyperplane that will maximize here the distance between the points of the two classes. So this is just an interpretation of the linear SVM, so the SVM related to the definition of this hinge loss function. It was just to give you some an overview of how to synthesize, and if you see here, the formulation of the SVM problem is very similar to what we say previously. So you have here a loss function term. So you will introduce here an hyperparameter C that we call the cost function, the cost variable, where you have two terms. So these first terms will try to you want to minimize the error, the classification error, and these CY, as I said, are related to the hinge loss. And at the same time, you want here to maximize the margin. And as you say, this is related to the regularization terms that we introduced before. So again, so you will be in the same configuration as a standard problem where we have a classification error term and a regularization term. And in this case, you have here introduced one hyperparameter. I mentioned that as T2 in my previous slide. So this parameter here needs to be tuned by the user. It's not a parameter that you will learn during your training step. So which are the two parameters that you will learn during the training step at this stage? The parameter θ1. Which are θ1 here? W, yes?
W
and B, right. So as we said, I'm seeing I lost everybody now. We are trying to find the equation of this plane. So this plane is parameterized by W, the normal here to the vector, and B. So B represents the distance here to the center. So your optimization problem is trying to find the best omega and B that will here minimize this problem. And so in this situation, as you say, C is not one of these hyperparameters. So omega and B are parameters θ1, whereas C is an hyperparameter belonging to the class of θ2 regarding my previous slides. I jumped some steps, but in the support, I just want to make here some reference. In jumping some steps, we can show that the equation of the hyperplane here will be, in fact, can be expressed as a summation here of the scalar product. Here you see the scalar product between xi, this is a training point, and your point of interest. Suppose you want to decide, you have a new test point, you want to decide to estimate the decision, the distance to the hyperplane. So it will estimate it by a weighted sum of the scalar products here between all of the training samples and x. So what is, in fact, the value of W regarding this expression? We say that fx is W transpose x plus B. So what is the value of W, in fact? Okay, yeah. Okay, W is a sum of alpha E YE, okay, and here, XE, okay? And we can see, so here that alpha are what we call the Lagrange coefficients, so I won't go into details. But what is interesting is that if these Lagrange coefficients are learned by the model, and you can see that, in fact, in the situation, if the points, you have different class of points. If the points here, I have an illustration of an hyperplane, so it's not a linear one in this situation, as you can see. And you can see that all the points of all of your training points that are correctly classified will have a Lagrange coefficient equal to 0, whereas all the points that are not exactly correctly classified have a value of the Lagrange coefficient that is inferior or equal to C. What is C again? Is my hyperparameter θ2 that I said before. So it's the value that I said by the user. So it means that, in fact, the equation of your hyperplane will be only dependent on what we call the support vector, because all these good points here are just, they will have an alpha null, so they won't have any impact on the computation of the weight here. But so the equation of your hyperplane will be only dependent on those points here, which are on the margin here, the yellow one, and those points here that are misclassified. So when they are misclassified, they can lay her in between the two margins or be really misclassified from any part from the margin here. So this is an important point, that in fact, first thing to remember is that in this situation, the equation of the hyperplane is delimited here by a summation of a scalar product between your training points. It's one point to remember, and that only one small part of your training data point will serve to compute this computation between because most of the points will be here, have a weight and a coefficient, a Lagrange coefficient of 0. So why is it important to focus on this expression? Is, as I said, in many situations you try to find a linear hyperplane, okay? Because it's simple. You will only have two parameters to estimate, omega and b. But in some situations, as here, for instance, you can see that a linear hyperplane won't be able to solve your problem. So in that situation, what we try to do is try to rewrite this problem so as to be in a situation where you will be able to find a linear hyperplane. So what do I mean? In that situation, for instance, you will try to find, instead of say, okay, I want to find f that will be a nonlinear function, very complex with lots of parameters, the simplest thing to do is, okay, I want to change my representation domain. I want to jump from the original description domain here to another dimension, to another space, where I can find a linear separation between my points. So this idea is that you will try to find a mapping function here that will map your data from the original feature space here to another space, what we call the representation or redescription space of higher dimension here, where in that situation, as you can see, for instance, here, you will have a clear separation between your blue and red points. And in that space, you can make reasonably the assumption of linear separation and build the hyperplane that will make this separation. So it's generally what we want to do is to jump from the original space to another space where the problem becomes simpler. I don't want to go into detail of how you can do that, but the only thing is, if you do that in the case of support vector machines, you will see that in that situation, the expression of your hyperplane will depends is the same expression as you have done before. As you say, we have some scalar products in the linear case between x, y, and x. In the case where you first projected your data in another representation space, you will have the same equation, but in that situation, it will only be based on the scalar products between the pairs of vectors, but in the description space. So it's very similar. And it's at this, we will use that to do what we call the kernel trick. So the idea, okay, say, okay, I have to find phi, project my points in this new domain, and do the computation. We don't like really to do that. Instead, we want we will do what we say the kernel trick. So instead of defining this projection phi, we want to associate. We will associate what we call a kernel function to this projection, which is a similarity function and which is equal, in fact, to the scalar product. So k between xy and xg here is equal to the scalar product between the projected xy and the projected xg, so in the higher dimension space. So the idea is to define some specific function that will be associated to this projection function. So in fact, this function have to satisfy some properties which are referred to as the Mercer condition, and I don't want to go into details because I'm not an expert in that domain, but this function have to have some properties, so it's not related, so it's symmetry, for instance, and positive definite function. But the idea is what you see here is that in that situation, you will see that here the kernel function will operate in the original space directly on the xy. So you won't have in this situation to compute the scalar product. So here, again, here is the optimization problem that you get. But what is more important is that in that situation, the decision function has this shape. So it's only related to the kernel function, so the similarity estimated in the original description space. And so in that situation, with the kernel function, is that the computation will be performed in the native space. The projection phi doesn't have to be explicitly formulated, and you can consider very complex projection function that potentially project your data in a description space of infinite dimension. And so only this kernel function is only constructed based on some Mercer condition. So basically, for us, generally, when we're doing nonlinear, we want to compute nonlinear hyperplane, we generally refer to very simple kernel function. Here I listed the two most used kernel functions. So polynomial kernels, for instance, and the Gaussian kernel that is very generally used. So another condition. As you say here, for instance, if I define the Gaussian kernel, I have here to define here the extent, the standard deviation, which will parameterize the full width of maximum of my kernel. What is this parameter, sigma?
Variance?
Yeah, the variance, but so should I learn it? No.
You will use it as a hyperparameter.
It's another hyper. It's a new hyperparameters. So if I want to do now nonlinear SVM, I will have those two hyperparameters to set, the cost variable C, and for instance here the sigma, the value of the sigma. If I choose a polynomial kernel here, I again have the degree of the polynomial to fit. And it's something that will be decided by the user. So here I have an example for the very standard moon dataset. An example of, here you have the similarity matrix. So here you have all your xy and all your x, so the different points. And you have the corresponding k, xy, xg for the different groups, so the two classes of the moon dataset. And you see the impact of varying sigma on the similarity you will estimate between your different data points, for instance. So, and as you can see, this kernelization trick is what we call kernel machine. Here I give some information about SVM. I show you on the SVM application how you can go from a linear model to a non-linear model. But this kernel trick may be applied to any kind of other function. For instance, if you are considering discriminant analysis, so I won't detail discriminant analysis in this lecture, but you also can have kernelization, for example, also of logistic regression. So it's a way to go from linear to non-linear function. And I think in this talk I didn't cover, just to conclude now, I didn't cover, so I mainly focused on the minimization of the classification risk based on what we call the discriminant model. But there is another class of model based on the minimization of the risk, which are called generative models. And as we said, we don't like really much estimating the joint probability, sometimes tricky. But there are some models that will, instead of parameterizing directly the decision function, that we try to estimate here the conditional probability. So the probability of observing xy, assuming that we are in the class K, for instance here, and that they will model this probability, this conditional probability distribution. For instance, they will make some Gaussian assumption. They will learn this conditional probability on the training database, and then they will use the Biosphere theorem to estimate directly. So the decision function will be the probability, for instance, that simple sample xy belongs here, for instance, to class 1. So in that situation, so you will estimate this information by making some assumption on the form of your distribution. So here, this information you can get because it's conditional probabilities. So assuming that you have sample from class 1, you will estimate the probability of observing xi, for instance. So you can parameterize this probability distribution based on your training data, feed the parameters, and then use this theorem to derive directly the probability. So contrary to the previous classes of function, here you will directly estimate a probability of belonging to the class. And again, as I said, then you will have to make a decision based on this estimation. And now, I think I will give the speech to Rémi for the following of the presentation. Thank you for this attention, and I think we make a conclusion this afternoon on this part all together.
Okay, good morning, everyone. So I will continue before the break. So I will mainly talk about decision trees, which are another model to do machine learning, and neural nets, but I will be very brief on neural nets because most of the summer school is dedicated to that. in some sense with deep learning, so I will try to not take too much of the presentations that are coming tomorrow and the next days. So let's start right away. So decision trees. The motivation of decision trees is that often in many domains, and including medical domain, you have some rules that you create based on observations. So for example, based on expert knowledge and clinical evidence, in the medical domain, you will say, I will need to measure this feature or this characteristic or this property, and based on the statistic that I observed, I will put a threshold to say if this person is at risk of being sick or something like this. So here you have two example decision trees taken from the medical domain. I don't know the exact content, but it's real data that has been created from clinical evidence. So the main aspect is that it will use elementary features and some manually set thresholds on the values of these features, basically. So what is a decision tree in the domain of machine learning? It's mainly the same thing, so we will use elementary decision rules and combine them in the form of a tree. So here you have a simplified example. On the left, you have the decision tree. On the right, you have the pseudocode that would do the same thing as the decision tree. So the decision tree is saying, okay, I look at the age of the person. If it's below 18, then I say it's okay. So here it's an example, a fake example for a sport practice. Let's say if you're below 18, it's okay to do sport. If you're not, then you will have a look at the type of sport. If it's a contact sport, then maybe you need to do additional tests for the eyes, for example, because you risk to have strokes at the head or something like this, and so on. And the decision tree basically builds a decision function that is more complicated and that successively will look at different features and apply different elementary rules. So in computer science, what is a decision tree? It's a model, and exactly in the same vein as what we've seen before, it's a model that maps an input X to an output Y. So basically, it's something that will model a function. But it's also a tree-shaped representation. I won't detail too much the language, but you have nodes and you have leaves. Leaves is where you're at the bottom of the tree in the previous representation and where you take a decision. And here we find our important aspect that it will, in the leaves and in the nodes especially, it will use only one feature of the input point. If my input point is X, then it will use only one feature, for example, X8 in the example here. And it will look at a simple rule for deciding whether this coordinate is smaller than a threshold or bigger than a threshold. And each leaf will be very simple. For example, each leaf is a decision that is pre-made, and we don't make complex things in the leaves. All the logic is basically in the nodes. And when we have this, we have a decision tree that allows us to compute this function. Simply, we take our input point, we start from the root, and we make the point go through the tree in order to decide in which leaf we will go by just looking at every split node, so every node, to see what decision we should take. Is the age below 18 or not? I go on the left or on the right, and so on. So this is just a model for a function. I take an example quickly here. You have a data set, binary classification again, and I spare you the details, but if you learn a tree, given that it's always a threshold on the coordinates, here we have two coordinates, we will have something that decides like this. So for example, it first decides to look at the vertical coordinate. If it's below 1.5, it will do something. If it's above 1.5, it will do something. And then below 1.5, it will look at the second coordinate, the horizontal coordinate. If it's below 1.8, then it's a triangle. If it's above, then I will still have to look at something else, and so on. So this is a decision tree. This is the case of 2 dimensions, but in any space with more dimensions, you have the same thing. The thing is that if you want to learn a decision tree, you have data, you want to learn it. usually, in the past, people would do it manually, probably at some point. But today, what you do is to use machine learning in some sense. But basically, what you want to do is to use your data to actually build a tree that is the best. The thing is, sparing you the details, finding the best tree is basically very time-consuming and too complex to do it. It's called NP-complete in the precise term. So we have a heuristic approach that will create a tree that is not the best, but that is not so bad in general. So what we will do is take our complete data set, all our examples. Again, it's supervised learning here also. So all our examples of people, let's say, with their label, whether they are sick or not, for example. And what we will try to do is to build a tree from the root. So we start with the complete data set, and then we try to find a good criteria that will split the points, so the people, let's say, in a way that is not so bad. And then it will give us two sides. So part of the data set will go on one side, part of the data set will go on the other side, and then we recursively build the tree with these sub-data sets. I come back to the previous slide. So I start from the complete data set, and then I decide to cut here because probably on top I see that there are more blue points than at the bottom, and this first cut, this first split is not so bad. Then I will take the data set from the top only, and I will see how I should split again. And that's why I get this dotted line here, another split that has been decided only with the points from the top. And on the bottom side, same reasoning. This split seemed not so bad. On the left here, everything was fine. On the right, I needed to split again, but I look only at the points that are remaining to do that. So that's how I build the tree, successively from the complete data set to smaller part of the data set. So in the few next slides, I will try to explain what is a best tree. So what is a good split that we choose in this procedure. So imagine you have this data set, 4 pluses and 2 minuses, and you have 3 different possible splits. So you try different features with different thresholds, and then you get these 3 possible solutions. So according to you, what split is best? Which one? Depends on what? Okay, depends. So can you say something about these 3 situations at least?
I think that B is the most.
Okay, B might be the best, okay. So one thing for sure is that A is bad, because A is not better. The split doesn't bring you much to the table because it's mostly the same distribution of points. So in both leaves here, we have bad situations where we don't really know what we have. We don't know better than before. So between B and C, we might discuss it, but we will see one answer in a few seconds. So the goal is to give a rule so that we can decide between these splits, basically. So what we will do is to use what we call entropy. So we will say that we want a split that creates subsets that are as pure as possible. So a good subset is a subset where there is only one class, for example. A bad subset is a subset where there is a mix, an equal mix of both classes if we are doing binary classification. So we want leaves that are, at least children of the split that are at least as pure as possible. So what we use is entropy, which is a concept of information theory that measure, in some sense, this pureness. So the entropy is this formula, so it's a sum of P log P, so where P is the proportion, let's say, of each class. So I will have an example just after. Here, you have, for example, this set. I give you different sets, so these are not splits, they are just set of 6 points. So a a set with 3 pluses and 3 minuses will have a maximal entropy. So if you compute, sorry for the thing in front, if you compute the formula with sum of p log p, so you will have sum of 1/2 log 1/2 on the right, sum of, no, whatever, sum of 1/2, because you have half of pluses, log of 1/2 plus 1/2 log of 1/2, because there are two classes, we should sum for both. So that's what we get here. We get the maximal entropy. I cannot say it, but it's 1. At the opposite, if you have a set with only one label, so either pluses or minuses, you get the minimal entropy of 0. So it gives you a scale of what is entropy in this case for a set of points. And what we will try to do is to favor sets with lower entropy. So we want to minimize the entropy in this case. So if we take back our situation from before, so we have our initial data set with 6 points here. The entropy is the same, it's the same data set. So it's 0.92 because if you want, there is a probability of, or proportion of plus that is 4/6, 4 pluses over 6. So I compare to the rest. So after the split here, each subset has the same proportion, so the same entropy, so in average everything is the same. So this split on the left doesn't bring anything in terms of entropy. It was 0.92, it's still 0.92. So I will take this one first. So we start from the same example. We get these two sets. One is completely pure, so it has an entropy of 0. And the other is almost pure, but not so much. And this gives actually an entropy that is of 0.72, which is quite high actually. And when I compute the resulting entropy of this split, what I do actually is to average these two, but average taking into account the number of points in each. So making a very pure leaf here that is very small in terms of number of points is not so good. That's why this one, for this criteria, will be better, because this one is pure and it's kind of big, even if this one is not pure. But it's better than this situation here, where the one that is pure is very small. This is okay, the intuition of what is a decision tree, how we built it, and at least the intuition of this entropy, because I won't go into more details about this. So we cannot find the best tree because it's too much expensive in terms of computations. So what we do is we build it recursively by starting with everything and splitting the data sets, and then resplitting and resplitting in the same way you would do if you were given a data set. You would be trying to find the same thing. But to make it really formal, we need a criteria to decide what is a good split. And this criteria here is based on entropy, which measure how pure a set is in terms of classes. So this slide doesn't say much. It's just saying that what we try to maximize is the gain in entropy. So it's just a recap of what I've said before. So what we want to maximize is the gain in entropy. So it means it's the entropy that we had originally, 0.92, minus the sum over all the leaves. V is a leaf here. S, it will be S1 and S2, of the entropy of S1 plus the entropy of S2, weighted by the proportion of points in each set. So it's exactly what I said, it's just a recap. So once we've done that, we have now an algorithm to actually create a tree. And that's all we need actually in this case. Okay. So I'll try to be brief on the rest. There are other measures, because actually it's a choice that we make to use entropy. So this one is another measure. It's the Gini impurity index. I skip it, but it will be in the slides. It's just to let you know that there are other measures. So decision tree, I took a simple example graphically with 2 dimensions and 2 classes, but with decision tree, basically you can take as input anything you want and any mixture of features that you want. You can have features that are the age of a person, but also features that are very different binary features, whether the person had a given test or whatever. And in the same way, you can have many decisions. So you can do binary classification, of course, but you can do multi-class classification, rating, regression, multi-dimensional regression, count regression. I mean, whatever you can imagine, you can actually do with decision trees. It's one of the models that is the most flexible. Many models will need to work in a representation space that is kind of R to the power of D, some Euclidean space. But decision tree don't need that at all. So it's very flexible, and you can do mainly what you want with that. So decision trees, they are flexible, they are fast, and one of the interesting things is that they are interpretable. So if I create a decision tree, then most of the people from the domain can look at it. I mean, like you give it to a physician or whatever, they can look at it and understand what they do. So this is a big feature of the decision tree. However, they are lacking some things like robustness, and they are tending to overfit, so to learn by heart a data set, but to generalize not so well. And they are not exact algorithms in the sense that they are based on heuristic. We don't know what is a good tree, we don't know what is a good split, and so on. So to not overfit with decision trees, what you can do is to limit the depth of the tree. So not learn the tree as much as you can, but stop, for example, at level 2 or level 3 or something like this. Or another solution is to build a complete tree and then prune it by cutting some branches, the branches that are less sure, because they are probably manipulating too few amount of data. Another thing you can do that is used quite a lot is random forests. And why is it called forests? Because it's a set of trees. And again, here I will skip the details, but what you do, you take your data set and you will not learn a single tree, but you will resample your data set to get multiple data sets. On each of these data sets, you will learn one tree. And then your final model will be a combination of all these trees that you've learned. An additional thing that random forest will do is that they will select some random features. So each tree will be learned on a different data set, but also each node of a tree, each split that we make in a tree will be restricted to select things between a subset of the features. So it forces the tree to be some kind of more diverse than they would be if we just learn many trees from the same data set. So now you have an input point, once you have learned all your trees, that go into different trees. So here, M trees. And each tree will give you one leaf for this input point. And each leaf will give you a decision rule. So it could be predicting a class, a value, or whatever. And then you will combine these decision rules. For example, if you're voting for a multi-class problem, then your decision rule will be to combine the votes of the multi-class problems or the probabilities if they predict probabilities. So random forests are fast still. They are very robust compared to decision trees, but we lose interpretability by doing this because now you're showing your model to an expert and you say, oh, there are 200 decision trees that voted like this, and you don't really know why. I mean, you know why, but it's more difficult to visualize what decision was taken. So here an example from a person that is at this summer school, actually, of a decision forest that has been used on multimodal ultrasound images registration. I will skip the details to be able to slightly mention neural networks. which can act as the basis for most of the deep learning that you will have in this summer school. So I will try to be very brief. So a biological neuron is some kind of machine that will sum its inputs, so receive electrical signal, kind of sum them. And then if the intensity that is received is greater than a given threshold, the neuron will fire. So it will send a signal to other neurons that might be of interest to it, by it. So it's very complex. In the brain, you have billions of connections, so it's a very complex thing. And it's laid out in the brain in some very complex manner. So this has been of interest for many years in biology, neuroscience, and computer science, via artificial intelligence. So there have been different waves of interest for neural nets, but the most recent one is from 2012, let's say, where with the computational power that we had at this period, the amount of data that we had, we could start to learn very complex models that started to outperform most of other machine learning methods that were using more traditional things. And especially in everything that was around the signal processing, so images, audio, video, or different kind of temporal data also. So you will see this again later. So take this as a thing that help you understanding later if you don't know about it. So the single neuron model, let's say the Perceptron for some shortcut, is something that takes inputs, so x1 to xn, that sums them. So you have here W, it's a bias. It's the same as the B in the previous slides for the SVM. You have here the same as an SVM, which is a linear combination of the inputs with some weights. So whatever you've seen before with the margin separator and things like this. So here it's exactly the same interpretation. You take the input, you do a linear combination of the values with some weights. You add the bias, you get a value, and it's a kind of score. So in the Perceptron, let's say, what we have after, it's also an activation function that will just take this value that is computed and map it to something else. So usually what we have is now the green one, rectified linear unit, but for the sake of this explanation, we'll consider the sigmoid that maps a value that can be any real value, and it maps it between 0 and 1. And you can, with this, easily imagine that it's a probability as an output, for example. So you can do this multiple times in parallel to have multiple outputs here. So basically, each output will have different weights. So here it's the same formula as before, but to illustrate that the weights are different. So this output is the combination of the inputs. This output is also a combination of the input, but they use different weights. If they wouldn't, it would be pointless, actually, because they would be computing the same thing. So this is the model for a single neuron. So here I put two single neurons. So I have two outputs here. And at the beginning of deep learning, what you have is what we call the multi-layer perceptron, and here it's with 2 layers. So we combine neurons, like 4 output neurons here, that we actually combine in an additional layer. So we put another neuron that will combine the output of the previous ones to finally produce the output. So I don't have time to show you this. You can go further and add more layers like this. And what you will see a lot more of this later. That's why I allow me to skip it fast. So what we know is that with just 2 layers, we can approximate any function that we want. So actually, the input, some hidden neurons, so some neurons that just take the input, and then some output that combines the hidden neurons. So this is sufficient to approximate any function that we might want to approximate. But you will see that in all the models, we prefer to have more than one hidden layer and to have something deeper. So that's what we call deep learning, actually. So all this, but you will see it again, is learned by gradient descent. So here you have your parameters theta, which represent all the weights of all your neurons. So it's the same as theta 1 in the previous talk, and it includes all the weights, so the W's from my slides. And we optimize exactly the same thing as in the previous talk. So the sum over the training set of a loss function that compares the prediction of the network, the neural net here, and the expected output. And that's what we want to optimize. We want to find the best parameters to minimize this cost function, this loss. So here, how do we do it? It's called gradient descent. We start with a random set of parameters, or something better if we can. And then we apply a simple rule that says the next set of parameters is the previous one minus some constant that we have to decide, an hyperparameter theta 2, let's say, times this complex thing that is that is the gradient of our loss function. And the idea is that if we start somewhere, we want to minimize, we will follow the slope to actually go in the proper direction, so we reach at least a local minimum here. So here are illustrations from Wikipedia on gradient descent. So here you have level lines of a function, and gradient descent will try to go to the bottom of the function, to the lowest point. So here it's a slightly more complex function. You see that it might be very complicated, and you will go, depending on where you start, you will go to different optimum. I skip this because I guess it will be mentioned later. And that concludes my talk. Slightly compressed, but you will see a lot on deep learning and neural nets later and tomorrow. Thank you.